morning, everyone. Hope you're doing well. We are moving into the third week of the semester. We got a bunch of labs turned in. Let's see. Over the weekend, 22 on lab 1 and 20 on lab 2. There are, I believe, 26 of you. So there are a couple people who haven't turned the labs in. So please, if that hasn't happened, talk to me because I don't want you to be missing those points. I'm going to say it. If you don't turn labs in, your grade will suffer. And there's nothing worse than having a student who's getting like B's on the tests and I end up having to give them a D in the class because they haven't turned a lab in. And I know how it goes. I see it pretty regularly with people who don't turn the first lab in, then they don't turn the second, then they don't turn the fourth. And then they're like, they have this grandiose idea of, oh, I'm going to catch up on 8 weeks of work and then move forward. I'm going to do a great job. I would just stop that mindset right now. If you didn't turn the first 2 labs in, and they're like they're ready, you just don't know how to submit them. That's one thing. But otherwise, start working on the next set of labs and get those done. And if you have extra time, go back and work on the first ones, but don't try and play catch up because it doesn't seem to work. So let's try and get this right now, get on the right track right now, get those turned in because I'm telling you, it will hurt your grade. And if you get to a place where you're not turning any of them in, it can decimate your grade. And I don't mean to scare you guys. I'm just want to make sure you're turning stuff in. Okay, so we're moving to chapter 3. This will be the final chapter that's covered on your first test. Your first test is not this Sunday, it'll be next Sunday. So we should have more than enough time to go over chapter 3. We may even start to like creep into chapter 4. Come on. Sorry, give me just a sec. Everything is moving especially slow today. There we go. All right. So this chapter is titled Matter and Energy. So we're going to take a little bit of a break from math, and then we're going to come back and do some math towards the end of this chapter. But we got some concept-based stuff to go on here. So if we were to think about, the universe as a whole, so everything in the universe, we would kind of put that at the very top of a flow chart, and then we would cut that into 2 sections, one of them being matter, and then the other one being energy. Matter is the stuff that the universe is made of. Energy is what gives matter behavior. It's what gives it oomph. It's what allows it to move and change, gives the universe a dynamic quality. This picture is upsetting to me, so I don't even want to talk about it. I don't know what the point of that is. Okay, let's do this one. So classification of matter. So if we move into the matter component, like what is the universe made of? We'll leave why it moves and all that for later. But right now, just talking about matter. In order to be classified in matter, it needs to have some sort of mass, even if it's a very, very small amount, like a gas. And it has to occupy space. Even if it occupies a very, very small space, like a single atom, right? Doesn't have very much mass. It doesn't occupy a whole lot of space, but we would classify that as having a certain amount of matter. I'm trying to see if this chart doesn't really have a flow chart. So hop between here and over here. All right, so we've got the universe. We divide that into matter and energy. Over here, we're going to talk about matter. So let's put that at the top. In order for that to be classified, it needs to have mass and occupy space. So that pretty much encompasses all the stuff. Now, we want to be able to classify matter into smaller, more specified components, because just saying, oh, it's matter, well, that's talking about a lot of things. So I'm going to make two arms off of this. On the arm over here, I'm going to say pure substances. And then over here, I'm going to say mixtures. So now we can narrow down matter as being either a pure substance or a mixture. And let's talk about what those two things are. So a pure substance is going to be anything that has a fixed or a definite composition. So that can be either like an element, copper, for instance, it's just copper, or it can be a compound, and we'll break those up in a second, but something that has a specified chemical formula. So let's say we have water. Water is hydrogen and oxygen, specifically 2 hydrogens for every 1 oxygen. Ava says her screen is showing only the beginning slide. Is anyone else having trouble with that? No? Looks like other people are doing okay. Ava, if you want, you might want to sneak out and come back in. Now, a mixture will have 2 or more different substances, and a substance could be a pure substance. It could be an element, or it could be a compound. The 2 or more things are physically mixed, but they're not chemically bonded to each other. And so in a mixture, I can change the proportionality of my constituents. In a pure substance, I can't change the proportionality. If it's water, I can't make it like 5 hydrogens to every 1 oxygen. It has to be 2 hydrogens for every 1 oxygen. In a mixture, though, if I have a balloon that's filled with hydrogen and oxygen, I could add more hydrogen and take out some of the oxygen, because in that case, they're only mixed. So let's break pure substances down. So pure substance classified as anything that has a fixed or definite composition, meaning that you can write it with a chemical formula. It has a specific definition. An element is something that's composed of only one type of atom. So over here, we've got an aluminum can. This would be an example of something that's elemental. It's just a series of aluminum atoms. Can I change the composition of this or the proportionality of it? No, it's all aluminum. It's 100% aluminum. A compound is composed of 2 or more elements, but they're in a fixed proportion and they're chemically bonded to each other. So let's add these 2 guys to our chart. So we're over here with pure substances. We're going to add elements. And we're going to add compounds. I think where people get confused a little bit is this here, the compound and the mixture. Those are 2 different things. This has a fixed proportion, a fixed chemical formula. Mixtures we can shift around. So how many types of elements are there? That's up for debate, depending on the periodic chart that you look at, but it's around 118. Not all of those are necessarily natural. Some of them are synthetic or they're created in a lab under very specific conditions. But they're all the things that are on your periodic chart. So I've got a periodic chart over here. I've been using this one for a while now, starting to fall apart. You can get one out of your textbook. You can get one out of your lab manual. You definitely want to have a periodic chart handy though, moving forward in this class. So print one out, have one available, preferably one that you can write on. I think that is helpful. So here we've got copper. So a copper penny is made out of just copper atoms. Lead, aluminum, all of these are considered a pure substance, specifically an elemental pure substance. Here is some examples of a compound. All of these things can be written with these chemical formulas. So hydrogen peroxide is H2O2. It looks kind of similar to water, right? In that it's got hydrogens and oxygens, but look at its recipe. It's 2 hydrogens for every 2 oxygens. Water is 2 hydrogens for every 1 oxygen. Table salt is NaCl, sugar C12H22O11, water H2O. So all of these have a fixed definite ratio. If I want it to be hydrogen peroxide, if I want it to have the properties of hydrogen peroxide, it needs to be 2 of these and 2 of these bonded in a very specific order. How many compounds are there out there in the universe? So many, okay? Thousands and thousands and thousands and thousands. So you aren't expected to have every compound memorized. There is actually a very nifty system for naming these things. These are all like the everyday names. So sugar, you know, table salt, but we would be able to name these in a more systematic way using nomenclature, which we will do in maybe next chapter. You guys are going to learn inorganic naming. So if you took Chemistry 092, you're probably already familiar with that, but you're also going to do organic naming as well later on in the semester, which gets a little crazy. But back to this chapter. So compounds, anything that we can write with the chemical formula. Elements within a compound. So a compound can be broken down into simpler identifiable elements. So if I have sodium chloride, which is table salt or NaCl, I can break that down through a chemical process into sodium and into chlorine gas. So one thing that separates our compounds from our elements is that a compound can be broken down. An element, though, like for instance, sodium, can't be broken down into a simpler identifiable material through a chemical process. So I can't take sodium and, you know, if I break sodium down into its subatomic particles, it's going to be made of protons, neutrons, and electrons. If I take chlorine and I break it apart into its subatomic particles, there'll be protons and neutrons and electrons. And this is kind of cool. The protons in sodium and the protons in chlorine are the same exact protons. It's the number that changes the properties. So I can't break these guys down, but I can break a compound down. If we go to that other side of our chart, we have a mixture. So these are going to be 2 or more substances, 2 or more pure substances that are physically mixed, but they're not chemically stuck together. So it's like taking 2 things and putting them in a container. We can change out the proportionality. And in this case, with mixtures, they can be separated out through some sort of physical method. So over here, I've got a liquid that has some solid mixed in with it. I can pour this through a filter with filter paper and collect the liquid and leave the solid behind. There's a couple different ways that we can do physical separation. You cannot physically separate a compound. So if I have, you know, for instance, table salt, NaCl, I can't put this through filter paper and expect one to go through and the other one to stay behind. If I want to break these 2 apart, I have to do it in a chemical reaction. So the 2 different ways that we can classify mixtures is a homogeneous mixture or a homogeneous mixture and a heterogeneous mixture. So let's add that over here. So we've got heterogeneous and homogeneous. Oh, come on. Usually this thing automatically snaps the box into a better looking shape. It's not working for me today. All right, so mixtures, we've got homogeneous mixtures and heterogeneous mixtures. Here is a homogeneous mixture. So this is actually a homogeneous mixture of two solids. Brass is combining copper and zinc together. A homogeneous mixture is going to be evenly distributed or mixed throughout. So the root there being homo, or the same. So salt water is a good example of a homogeneous mixture. This one is a little bit, I don't see that quite as much, but it's something that's just evenly mixed throughout. So if I was to sample at the top of the salt water sample or the bottom, it would have like a similar, relatively similar proportionality. Here's another example of a homogeneous mixture, a homogeneous mixture. So breathing mixtures for scuba diving. So we've got nitrix, which is oxygen and nitrogen gas. There's some other ones that have some other different gases. These are evenly mixed. That's super important that they're evenly mixed, right? If they weren't evenly mixed, let's say that the oxygen sat on the bottom and the nitrogen sat on the top, and then you're sitting somewhere in the ocean breathing and you're just getting full hits of nitrogen and no oxygen, you're gonna pass out, right? So this has to be evenly mixed. A heterogeneous mixture, on the other hand, is something that they're like two things put together and they're not evenly mixed. So here's water and some copper pennies. If I was to sample from the top here, it's going to be like 100% water. If I take a sample from the bottom, it's going to be like 85% metal or copper and like the remaining part water. So it's where you have different parts in the mixture and they're like visible. You can see it. Oil and vinegar is a really good example of a heterogeneous mixture. Bananas and oatmeal. Something where the sample isn't smooth and continuous. So here's that flow chart. You want to be able to classify matter in these lower compartments. So go ahead and identify these as a pure substance or a mixture. And then actually, I want you to also classify them as either an element, a compound, homogeneous, or heterogeneous. Okay, so pasta and tomato sauce. That's definitely a mixture. Every bite's going to be slightly different. And And because every bite is slightly different, we're going to say that this is a heterogeneous mixture. Aluminum foil, that's a pure substance and made out of just aluminum. So we're going to say it's an element as well. Helium, it's an element. It's a pure substance. Air, that is actually a mixture, and it's a homogeneous mixture, evenly mixed of, what we have, oxygen, nitrogen, argon, some CO2. So they told us mixture, pure substance, make sure we went a little bit farther with that one. These are all mixtures, and it says classify them as homogeneous or heterogeneous. So are they the same throughout, or are they have differences from where you're sampling? So hot fudge sundae, that is definitely a heterogeneous mixture. It is different throughout. A hot fudge sundae, that's the situation where like my daughter will eat all the fudge off the top and leave the ice cream behind. Shampoo, we hope that that is evenly mixed. We hope that the chemicals in our shampoo are evenly distributed and mixed. You don't want to get a squeeze that contains, just all the kind of icky bad stuff in it. Sugar water, as long as it's stirred, right, and it's not a saturated solution, it should be evenly mixed. Peach pie, we would say that that's heterogeneous, right, different, depending on where if you're more of a crust person or more of a filling person. Okay, so once we've classified our matter into being, a pure substance or a mixture, so and so, we want to also be able to define what state the matter is in. And we also want to be able to classify some of its properties. So here we've got, these are drying vats. So they take seawater and they put them in these vats and they dry it out, and then they can collect the salt from it. So solids, where my brain is today, it's not with me, sorry. So the three states of matter that we're going to be looking at today are solids, liquids, and gases. There is another state of matter outside of that called plasma, which actually a lot of the universe is made out of plasma, but it is not a state of matter that we see on Earth in our everyday life. So we're going to leave plasma alone and just look at solids, liquids, and gases. So if you're a solid, this is a chunk of amethyst over here, which is just purple quartz. You're going to have a definite shape and a definite volume. The reason that you have a definite shape and a definite volume is because the atoms or particles within your material are close together and they're fixed in their arrangement. So there's not a whole lot of space between adjacent atoms, and the adjacent atoms, like soldiers in an army, are going to line up. They're going to face a specific direction and they're not going to change that direction. Astrid, is fire plasma? Yeah, you see it there, but we're not gonna get into the whole process of that. So other things that happen with solids, particles move relatively slowly. So even in a solid, like everything is moving. All particles have some sort of thermal energy or vibrational energy. The atoms in here, they're fixed, but they're sort of like vibrating just a little bit, right? So we've got these soldiers in a row and they're standing still, but maybe like, they're wiggling their finger or their toe or something. So there's a little bit of vibration happening, but not enough for the adjacent atoms to move past each other or break apart. Liquids, on the other hand, how do we go from a solid to a liquid in a given type of material? There's a couple different ways you can do it, but one thing is you can heat it up. So you add energy to the system, and those soldiers that are sitting next to each other in this fixed, rigid shape start to vibrate even more. And in a liquid, the kinetic energy that we've put into it allows the adjacent particles, whether they're molecules or elements, to start to move past each other. So we have a definite volume, but we have an indefinite shape. Here's some water. If I take water from a bigger container and pour it into a different shaped, smaller container, the volume will stay the same, right? 100 milliliters in a big jug and 100 milliliters in a small jug, it's still going to be 100 milliliters of water. You're not going to create more volume of water, but its shape will change. The reason that its shape changes is because the particles are now mobile, so they can roll past each other. But the particles are still very, very close together, so they aren't going to change in their volume. The particles move slowly, not quite as slowly as in solids, but slower than a gas. If we add even more heat to our liquid, we will become a gas. Gases are a really unique substance. A lot of times chemistry classes will spend a whole chapter just talking about gases. They have an indefinite shape and they have an indefinite volume. So gases will not only change their shape, they will also change their volume, meaning that they're compressible. The reason that we have this is because the particles within the gas are very far away from each other. They take up a really broad volume. And they don't really interact with each other because there's so much distance between the adjacent particles and because they have so much energy that they kind of fly past each other without really like even connecting or talking to each other. It's kind of like when you've had too much coffee and you're in a hurry to go somewhere, right? And people are like, hey, how are you? You're like, I'm fine, I gotta go. You're not clumping together with your friends. You're just on a mission. So all these particles are doing that. So because they're not clumping together or attracted to each other, if I was to say open this balloon in a room, all the particles are going to expand and fill the entire space of the room. Okay, and then if I was to open that room to the rest of the house, those particles would then expand to fill the house. So in a gas, gases will always take up the shape and the volume of whatever container they're in. Because of that, gases can be compressed down. So I can take the gas that fills up this entire room and I can put it into a small canister. So here is sort of a summary of all of that stuff. You will want to know those things. So let's do a little study check here. Hopefully a lot of this feels sort of intuitive, but identify each description as being either a solid, a liquid, or a gas. Just give you all a minute for that. So you don't need to write it all down, but just take a mental note of what you think each one of these is. Okay, so a material that has a definite volume but takes the shape of the container, that would be a liquid, right? We can't change the volume of the liquid. If it's 100 milliliters, it will be 100 milliliters no matter what container, but it will move to fill the shape of the container. Particles are moving rapidly, that would be a gas. So gases have a high amount of energy, thermal energy. Particles fill the entire, the entire volume of the container, that would also be a gas. Only one that can do that. particles have a fixed arrangement, that would be a solid. Liquids and gases, the particles can move past each other. Particles are close together, but moving randomly, that would be a liquid as well. Oh, I'm sorry, did I say particles have a fixed arrangement? Yeah, that would be a solid. Okay. So depending on what matter you're looking at, like if you're looking at copper or you're looking at aluminum or you're looking at water, each compound and element and also mixtures will have specific physical properties. And a physical property is some sort of unique quality that that type of matter has, that it shows you without having to undergo a chemical change in order to show it to you. So it's not having to change the identity of what it is. So things that represent or show us physical properties, so shape, physical state, like boiling and freezing points, density, color, those are all things that matter can show you without having to become something new. So gold has a shiny luster. Gold doesn't have to undergo chemical change in order to express its shiny luster. It's just a physical property that it has. Water boils at 100 degrees Celsius. It doesn't have to become something new in order to show you its boiling point. It does have to show its phase, it has to phase change. It has to move into a gaseous form, but it doesn't have to become something new. It's still H2O. So looking at these copper pots over here, they have a reddish orange color. It's still copper even after you've experienced its color. It's shiny, good conductor of heat and electricity. It's solid until about 25 degrees Celsius, and it's got melting and boiling points. All these things, physical properties. Identify the state of matter for each of these. We don't need to go over that. Okay. So a physical change, when something undergoes a physical change, it's changing its appearance, but it's not changing what it is. So a change in state, like going from a solid to a liquid or a liquid to a gas, that would be a physical change. A change in the shape. So let's say I've got a piece of paper and I tear it in half. Tearing it in half has changed its shape, but it's still a piece of paper. No change in the identity and the composition of the substance. So it's still what it is. If I take gold, let's say I have a hunk of gold and I melt it and form it into a ring, it's still gold. So examples of physical changes: water boils to form water vapor, still water. Sugar dissolves in water to form a solution. It hasn't become something new, it's just dissolved sugar. Copper is pulled into thin wires, paper is cut into confetti, pepper is ground into flakes. Okay, so the thing that you're starting with is the same as the thing that you're ending with. Might look a little different, but it's not an actual, doesn't have any actual chemical differences. All right, that we're gonna. Now, this has to be opposed to something else, right? So if there's physical properties, then there does have to be situations where you change what it is. And those are known as chemical properties and chemical changes. So chemical properties describe the ability of a substance to interact with other substances and to change into a new substance. So when you are expressing a chemical property, when matter is expressing a chemical property, it actually has to change into something new in order to do that. A really classic example of a chemical property is flammability. So oh, hold on one second. Sorry about that. Okay, so when we undergo, so this chemical property and chemical change, that kind of go hand in hand, but a chemical change will occur when there's some sort of change in the composition. So we have a starting substance and it turns into some sort of new substance. The new substance will then have its own new characteristic physical properties. So flan has a topping of caramelized sugar. Caramelized sugar is a good example of a chemical change. During a chemical change, we have some sort of new composition, new chemical properties, new physical properties. You can't undo a chemical change like very easily, right? So whereas if I have gold and I put it in, change its shape into a ring, I could technically put the ring back into the original block shape by melting it and reforming it. I can't undo this caramelization of sugar. It has been caramelized. It is done. It's a done deal. So here are some examples of chemical changes. We've got a silver reacts with air and it starts to get black and has like a grainy coating to it. It's kind of patinas. That would be a chemical change. A piece of wood burns to produce heat, ash, carbon dioxide, and water vapor. Yeah, you're not going to take the carbon dioxide, the water vapor, and the heat and put it back into that piece of wood or make it into that exact piece of wood again. Heating sugar to caramelize it, any sort of rusting or patinaing, anytime you have a metal and it's combining with oxygen and it you get a new substance gathering on the side. So I want you to try this. I want you to try and classify this as either physical or chemical, each of these 5 examples. Okay, so you can kind of think of when you're going through this, like, can I undo this? If you can't undo it, it's probably a chemical. So ice melts in the sun. That's a physical change or a physical property. We could, refreeze the water. Copper is a shiny metal. That's a physical property. It's staying the same thing. Paper burns, or paper can burn. I can't undo that process if I burn it. A silver knife tarnishes. That's a chemical change. Any sort of tarnishing, patining, all that chemical. A magnet removes iron particles from a mixture. That's a physical property. So it's not, the magnet isn't having to become something new in order to do that. So physical or chemical, again, burning a candle, that is chemical. We can't undo that process. A ice melting in the street, that's a physical. We can undo that. Toasting a marshmallow, any sort of cooking thing, that's all chemical. When you cook, you're doing chemistry. Cutting a pizza, that's physical. So it's still a pizza, it's just in smaller slices. Iron rusting on an old car, that is definitely chemical. All sorts of rusting. All right, let's see where we are. And I think we'll get through temperature. I might call that a day. So when we are measuring temperature, we use a thermometer. Temperature is measurement of how hot or cold an object is compared with another object. Temperature is really the measure of thermal energy within an object. So how much movement do the particles have within a material? Something like a solid usually has a lower temperature because it has less thermal energy in it. Gases will have higher temperatures because the particles are moving much faster. So when we have one of these thermometers, what's actually happening is like the particles are hitting the receiving end. If there are more particles hitting it, we're gonna have a higher temperature. So as far as temperature scales are concerned, we've got Fahrenheit, Celsius, and Kelvin. Fahrenheit is probably what you're most comfortable with, but we're gonna stay away from that. Quite often in this class, we're gonna stay more with Celsius and Kelvin. Each of these scales have specific reference points for boiling and freezing of water. Some of them, I think Celsius and Kelvin make more sense than Fahrenheit. In Celsius, boiling is at 100 degrees Celsius and freezing is at 0 degrees Celsius. Those are sort of easy numbers to remember. Kelvin is also a scale of 100 degrees from boiling to freezing within water. It's 373 for boiling and 273 for freezing. How we get from Celsius to Kelvin, if you can see here, you just add 273. Fahrenheit's a little bit different. We have to go through a stronger calculation to get from Celsius to Fahrenheit. In Fahrenheit, water boils at 212 degrees Celsius and water freezes at 32 degrees Fahrenheit. So those numbers are kind of like weird. Why don't they just use 0 degrees for Fahrenheit? Well, 0 degrees is on the Fahrenheit scale is a very specific saltwater solution when it freezes. So what is the temperature at which water freezes? 0 degrees Celsius. What is the temperature at which water boils? 373 Kelvin. How many Celsius units are between the boiling and freezing points? 100. So you want to know your boiling and freezing for water in each of the scales. Again, you know, if you're on an exam, you can probably just reference it. So have it somewhere handy in your notes. So you will have to do some converting between Fahrenheit and Celsius. Here is your one of your equations. This is to get if you have Celsius and you want to get Fahrenheit. Okay, so if you have to plug Celsius in, you take 1.8 times whatever your Celsius is and you add 32. Now, if we were to invert this equation, and instead we want to solve for Celsius and we have Fahrenheit, you'll use this equation down here. Okay, so there's two separate equations that are just turned in on each other. If you're good with isolating variables, you really only need to know one of them. You can solve for the other one. But if we want to get degrees Celsius from Fahrenheit, we have to take the Fahrenheit first, subtract 32, and then we divide by the 1.8. Kelvin from Celsius is much easier. Kelvin is just whatever your Celsius is plus 273. So you just shift everything over by 273 degrees. Why do we have this Kelvin scale thing? Well, because we can have negative numbers or negative temperatures in Fahrenheit and negative temperatures in Celsius. Those negative numbers can sometimes be problematic when we are running calculations. And I mean, think about what temperature is measuring. Temperature is measuring the random motion of the particles. How can you have negative motion, right? You can have zero motion, but a negative motion of the particles doesn't really make sense. So Kelvin gets rid of that altogether by shifting everything over, specifically Celsius, by 273. So when we get to 0 degrees Kelvin, this is sometimes called absolute zero. You won't have any negative numbers in a Kelvin scale. The lowest you can go is 0 degrees Kelvin, or absolute zero. That is the temperature at which all particles stop moving. Okay, so all the random motion that every adjacent atom has, all the vibration, even in the coldest solid out there, there's still a little vibration, that all ceases to exist at 0 degrees Kelvin. You can't get colder than that. We don't use a degree symbol too on the Kelvin. There are no negative temperatures, and the unit size with Celsius and Kelvin are the same. So 1 Kelvin is the same unit size as 1 degree Celsius. It's just shifted over. So if we want to calculate temperature or a new temperature, state the given, state what's needed. This may be a little bit overkill. You're just going to plug it into the temperature equation, right? So if I've got a person with hypothermia has a body temperature of 34.8 degrees Celsius. What is the temperature in degrees Fahrenheit? Because this for you might not be intuitive because we're so used to like 98 degrees, 96 degrees for our body temperature, but that's in Fahrenheit. So let's go ahead and convert this from degrees Celsius into Fahrenheit so it can make a little bit more sense in our mind what's going on. So we have our given information, which is 34.8 degrees Celsius. We're trying to find Fahrenheit. We need to use the right equation. We want to get the one where Fahrenheit is by itself. So in that case, it's Fahrenheit will equal 1.8 times your Celsius plus 32. So we literally just take this and we stick it right in there. So we'll take that 34.8. We're going to multiply it by a 1.8 factor, or sometimes they will write it as 9/5. Same thing, and then add 32 to it. So when we plug this into our equation, we get 94.6 degrees Fahrenheit. That may start to make a little more sense for you temperature wise. Okay, yeah, so if my body temperature is 94.6, that's pretty cold, right? We don't want to be dropping, below 96. So try this one out. On a cold winter day, the temperature is negative 15 degrees Fahrenheit. What is that in degrees Celsius? Okay, so always be mindful about which direction you're going in. So in this case, we're going from Celsius, or rather we're going from Fahrenheit to Celsius. So we don't want to use that equation we had in the previous one. We want to actually use this here, where Celsius is over by itself and Fahrenheit is embedded into the equation. So we're going to take our Fahrenheit, which is negative 15. We're going to subtract 32. and then we're going to divide it by 1.8. So we should end up with a negative number here as well, negative 26 degrees Celsius. Nothing crazy, just plugging and chugging. What is the normal body temperature of 37 degrees Celsius in Kelvins? Celsius to Kelvins and Kelvins to Celsius is super easy. We just add or subtract 273. If I'm going from Celsius into Kelvin, I add 273 to try and remove any possibility of a negative number. So we'll just take the 37, add 273 to it, and we end up with 310. So there will be lots of times where you're adjusting temperatures in this chapter. You'll just be able to do that. All right, let's see where we're at. Okay, so I think we're going to stop there for today because we have this week and next week. So we've got some cushion space. If you have any questions, please feel free to stay around. If you didn't get the lab turned in and you need some help getting it turned in, or you're like, oh, I've got it partially together, give me something at least for this first round. But feel free to stay around and we can chit chat about how to do that. Otherwise, I will see you all on Thursday. Enjoy the middle part of your week. Bye, guys. We've got a couple people still floating around, so I'm going to put you in a waiting room. Bring you in just a sec. LJ, you got a question?